Okay, here we go. Welcome to the June edition of Headingley Cafe Scientifique. Let's go on to the main event, and we're very happy and very pleased to welcome Heather Johnston, who's going to talk about the rise and fall of the giant planet occurrence rate. This is sort of like a transition of kind of a view of in astronomy. So, over to you, Heather. You all right, then?
Yep.
Good.
All right.
Good.
Hello, everyone. I hope you can hear me at the back. Please signal if you can't, and I'll speak up a little bit. As kind of introduced, I'm Heather Johnston. I work at the University of Leeds. I'm a PhD student, and today I'm going to be telling you about the rise and fall of the giant planet occurrence rate. This is part of my PhD project that I've been working on with my supervisor, Oya Panik, and one of our collaborators, Baby Leo, and he works at Zhejiang University in China. So, a little overview of some things I'm going to cover tonight. I'm going to give you a whistle-stop tour of some star and disk evolution, and then I will cover planet formation, which is my main area of study, and then I'm going to hopefully answer to you why I'm so interested in intermediate mass stars, why I'm so interested in giant planets in particular, and then hopefully by then we'll be able to put it all together and we'll establish the potential origin of the rise and fall of the giant planet occurrence rate, and then I will briefly touch on some future work that I'm hoping to do in this last year of my PhD, and then I'll leave you guys with a summary. And if you have any questions along the way, please feel free to shout them out and answer. I'd rather answer as I go along, just so that we're all on the same page and we can figure out what's going on. So, this is the nice figure that we usually use to describe this life form of a star. So right at the far edge here, we have something called a protostar. So all stars are basically a massive collapse of gas and dust that become gravitationally bound, and then eventually at the core of that it starts burning hydrogen into helium, and once that stabilizes and gets rid of all of these excess material surrounding it, it will evolve onto something like the main sequence. So right down at the bottom we have something that evolves into being a brown dwarf, and now brown dwarfs are a very special case, so they're very, very small stars and are technically failed stars, so they're like a very, very massive giant planet or a very, very bad star, and they basically live indefinitely, which is why this brown dwarf goes straight into a brown dwarf, because the ones that are born just live forever. They're so tiny that they just keep burning and burning. If we go up a notch, we get something that looks like another slightly more massive protostar. We get a red dwarf, and that red dwarf also has a very, very long lifespan. It keeps burning and burning, but eventually will exhaust its material and will become a white dwarf. And then once we get up to something like a sun-like star, which, like our sun, as you might think, will eventually have something that goes from a protostar. It will rid itself of that excess material, and then will start to stabilize, and it will go into something called the main sequence, which is the phase of life that our sun is currently in. And it will stay like this for around 10 billion years or so, and then eventually it will run out of hydrogen to burn and will become a red giant, possibly engulfing the Earth, but hopefully well beyond our lifetimes, and we'll expel that all out, and then we'll leave a planetary nebula behind, which is all of that gaseous material that is shed out and is now chemically rich, and then the thing that is left behind is a white dwarf, which is a hot iron core. And if we again kick it up a few gears, we get stuff that forms into blue supergiants, which is the very, very hottest end of stars. So blue, if you think about a gas flame burning, it burns blue because it's very, very hot. And eventually it runs out of material much, much faster, which is why these scales are shorter. It becomes a red giant, it can potentially shed more material, become a blue giant again, or it will undergo some sort of supernova event and then eventually become a neutron star. And then increasingly, as we increase this initial mass, we get larger and larger supergiants, and then more explosive events like type 2 supernova, black holes, and yeah. So basically, the more massive you go, the more violent the death is, and also the more short-lived the star is. The part of the stellar life that I'm particularly interested in is this protostar phase, and most importantly I'm interested in protostars around both sun-like stars and also sort of into the blue supergiant territory. So the ones that I'm most interested in looking at are stars that are the size of our sun or up to about 3 times as massive as our sun. So we're very much in this intermediate mass star range. So, talking about protostars, they basically have this massive material, of Nicholas clay, which would be nice. There we go. So basically the star is the thing in the middle, and then what we call a protoplanetary disk is all of this gas and dust surrounding it. So this has a two-part job of both feeding the star and basically providing the building blocks for making planets. So yeah, it basically spends an indeterminate amount of time. So we see that some stars will gather all that material in a very, very short amount of time. It will exhaust it and grow massive within sort of 5 million years or so, but we also find disks around much older stars as well. So this lifetime is something that is very contested in the astrophysics community and something that we are continuing to explore today. So in terms of disk, we start off with something that around a very young star that looks like this. So we have a very, very broad extended disk out here. There's accretion onto the central star, which is basically all that material flowing in and feeding the star. And then there's also irradiation by the star itself, which irradiates back into the disk, which also loses the material, because the goal of these stars is to get rid of its material because it wants to be by itself and be stable. So eventually we get something that looks like a settled disk, which means that we're starting to get these dust clumps forming, as well as material still being created onto the star, but it's also starting to lose it angularly from the very edges. A little bit further into this lifetime, we have EUV, which is a type of photoevaporation, which I will talk about in my next couple of slides. But basically, it's now the star is starting to eat away from the inner part of the disk and basically lose mass that way. And then eventually we end up with something called a debris disk, which is essentially like an evolved form of disk. So at that point, we're getting sort of planetesimals forming, which are the building blocks for making planets. Yeah. So here we have, there's 3 different kinds of photoevaporation, and photoevaporation is basically how the star gets rid of the disk because it wants to either acquire that mass or just get rid of it. So there is X-ray irradiation, which is very, very well constrained. We know a lot about it. It affects the disk quite wide distances and will just eat away at the material that way. There's FUV, or far ultraviolet, which operates at sort of a different wavelength, and what that does is it heats individual molecules, which then heats the disk in turn, which then makes it lose angular momentum and mass. And that's very dependent on the star and the location of the disk, so this isn't something that we've really well established. We know it exists, but we're unsure of how effective it is at making it lose material. And then lastly, we have extreme ultraviolet, which is sort of your classical disk evolution scenario, where it basically eats away at the inner disk first, and then around very, very close into the star, and then at that point, anything that is transported from the outer edge of the star, it can no longer go onto the star. But what I want you to take away from it, there's different types of photoevaporation, and they differ depending on the location of the disk and also the type of star that we're looking at, and that mostly amounts to how massive the star is. So I now get to go on to planet formation, which is my favourite part because that's what I study. So there are 2 main kinds of planet formation. So we have something like we saw before. We have our star, we have this protoplanetary disk surrounding it. And in order to form giant planets in particular, there are 2 main methods. So this one on the right-hand side is called gravitational instability, or top-down giant planet formation. So it essentially forms a little bit like how a star forms, a massive gravitational collapse of gas and dust, and then forms inwards and creates a very massive giant planet. And this is very popular idea or formation mechanism because we observe giant planets at quite wide distances from their star, and it seems quite hard to build planets that way. So that's the idea behind gravitational instability. However, for the purposes of this talk, I'm going to only be focusing on pebble accretion, and this is the traditional bottom-up method of forming giant planets. So basically you have dust grains that eventually become stuck together, they become slightly more massive, they then become something called a planetesimal, which is like something about a kilometre sized, and then those kilometre sized planetesimals crash into each other, forming a core. And eventually that core becomes massive enough that it can undergo something called runaway gas accretion. And what that means is the planet is so, now the rocky planet core is so massive within the disk that it can acquire its own pool of gas surrounding it, and that's what forms a giant planet that way. So for the purpose of this talk, that's what I'm going to be referring to as planet formation.
So one's sort of like big lumps forming, and the other one sort of lots of little bits together until they're big enough to
so one will be like very nicely dust and gas, how you might think originally how a planet might form, lots of rocky planetesimals, and then it will eventually become massive, and then all of this gas and noise surrounding it will be able to accrete onto it because it's now big by itself, basically. And then the other way is that you have very cold edges of the disk because we're very far away from the star. That becomes gravitationally unstable in itself, and it collapses inwards, and it forms these very giant, very massive giant planets. And it's sort of similar in the way that stars would form, except they're not quite massive enough that they would burn hydrogen to helium, so therefore they're planets. Yes, and there is also another form of pebble accretion or core accretion, which is called streaming instability. And I would like you guys to think of it as just like enhanced core accretion. So with core accretion, there's a lot of issues with the fact that when we think about building up these particles within the disk, we have tiny dust grains that have to go from being, millimeter size to something that is being kilometer size, and that's really, really hard to do, especially at different locations within the disk. So what we tend to think of, there's certain barriers that these planetesimals must overcome. So there's something called the bouncing barrier, which means that at a certain point, when you have dust grains with enough velocity and they're crashing into each other, they tend to bounce apart rather than sticking together. And obviously that's not very helpful for building a planet. So to overcome this, there's a certain formation technique called streaming instability. And what we think of it as is like gravitational instability, but on a very tiny scale. So what would happen was all of these dust grains would sort of collect together, and then they collapse inwards and form these planetesimal cores of being about a kilometer size. So this is essentially to overcome this issue that we see in experimental data. So it's just core accretion, but on a very, very fast time scale, which is very helpful for when you want to form giant planets, because the longer that you have, the more useful it becomes. So, now on to the planet part of the talk. So, as of June 2023, there are over 5,000 exoplanets that have been found in the NASA database. And that's pretty exciting for a field that only really had its first confirmed exoplanet in 1995. So it's a very, very young field, and it's a very exciting field of astrophysics. And the sort of planets that we see are very, very diverse and very interesting. So originally, when people were first taking observational data, we tended to find very hot, massive planets around stars, and this was definitely an observational bias at the time. So if you think about having a star, if you have something massive that's close in, that's much easier to see than something that's very, very tiny. But as the field has progressed and we put on more instruments from NASA and ESA, we've started to see that skew very, very more heavily to rocky planets being very much the norm to form around stars, but giant planets are far rarer than we originally thought. So that's really, really interesting, especially because, as we know, in our solar system we have Jupiter and we have Saturn, which are very, very traditional gas giants. So it's really, really important that we investigate why, and also did Jupiter and Saturn sort of aid our habitability on Earth, or did they potentially hinder it as well? So that's something I'm interested in.
So when you're talking about sort of giant planets, you're talking about Jupiters and that kind of thing?
Yeah, so anything Jupiter or bigger, essentially. So I believe that Saturn has about 90 times the mass of the Earth, so very, very massive, and Jupiter has about 300 times the mass of the Earth, so significantly bigger. When you think about terrestrial planets, think sort of Earth-size, Venus, Mars, Mercury, things like that, and then supergiants or super Earths or Neptune-like planets are obviously things like Neptune, which are sort of 10-15 times the mass of the Earth, and a lot of that depends on the ratio of rocky material to gaseous material, so that's how we define it. But there's a lot of debate to be had at where these boundaries start, since we only really have our own solar system that we can observe close up. So there are a couple methods of how to find planets. So the one that is probably the most straightforward is called direct imaging, and we found 67 planets with this method. So what we have to do is, because the star is so bright, we have to cover it up with something called a mask, and then that reveals the light of the planet. So this only really works if the planet is quite far from the star, otherwise it gets lost in that mask that covers it up. So it's not the most popular method of finding planets. The next one is transit, and I would say this is the most notorious one. We found almost 4,000 planets with it, and what that does is when we see a planet orbit in front of the star, it causes it to dim. So we measure the brightness, and from that we get something that looks like a light curve, which is in this bottom left-hand corner. And it's essentially like when we view the eclipse or something like that. So that's how we find a lot of planets. This is particularly good at finding Earth-like planets. So there's a system, a telescope called TESS, and that's predominantly what that does. It observes transits. And yeah, so this is very good for that type of thing. And this little divot can tell us how massive the planet is. And then the next one is detecting planets via radial velocity. Now, this is very good at detecting giant planets, but not very good at detecting other kinds of planets. So if you have a star, it obviously has a gravitational pull, but if you have a massive enough planet, it also has its own gravitational pull. So although the planet is dictated by the star's gravity, the star also responds to the planet's gravity, so it creates this little wobble effect that you can see in this animation. And obviously this is very good at detecting specifically giant planets, because they have more of an influence on their star, and it's also good at detecting very close-in planets, because the closer you are, the more influence that you would have from the star. And this also tells us how massive the planets are. And we found just over 1,000 planets this way. So I'm going to give you a brief case study in why it's so hard to find giant planets even around young stars, because as you've seen, the more massive they are, the easier they are to find. So one of the most famous young stars that we know of is called TW Hydra. So you can see here, this is the star right in the middle, and this surrounding it is a protoplanetary disk. It's a very young star. It's only 5 to 10 million years old. It's found in I think the Taurus constellation, I believe, and it's about 196 light years away, and it's around 80% the mass of the Sun. So very much a Sun-like star, so it would evolve the same way our Sun does. And it was a very famous case of misidentification. So in 2008, there was a very prominent article that was released at the time saying, oh, we found a really massive giant planet around this star. It's very close in. At the time, it was the youngest system that we'd ever seen a giant planet in, so it was very exciting at the time. Around, I believe it was even 6 months later, they had to publish a retraction saying it was actually a hotspot on the star. So this causes a really big issue, because these stars are very much in their sort of angsty teenage phase of hiding away, and also having very acne-ridden spots. So these spots are hot regions or cool regions on the star, and as the star rotates, it also causes these dips in brightness, or perhaps enhancements in brightness, which might indicate a planet. So they eventually had to do some additional study and establish that it in fact was not a planet, it was just a very large hotspot that was covering the star's surface. So you can kind of see how hard it is to be able to observe these kinds of things, and that's even with the very lucky scenario that TW Hydra is observed based on. So it means that we can see the star in it, and we can see the disk surrounding it, rather than it being flipped sort of flat. And since then, we have actually found a Neptune-like planet, which was detected at around 22 AU, so much further out in the disk. And this was done with ALMA, which is a series of telescopes in Chile that are specifically developed to view protoplanetary disks.
For instance, just to say, people don't know, astronomical unit is...
Oh, astronomical unit is distance from the sun. So the Earth is located at 1 AU from the sun, so it's distance from the Earth to the sun. And then if you think about 22 AU, that's way out beside sort of past Uranus, I believe. So quite far out in the disk. Okay. And here we have my favourite photo from the JWST release, which is Jupiter in the infrared, I believe, which is a very cool photo. So now we're on to why I am specifically interested in giant planets. So they contain the majority of the mass and angular momentum in a system, which essentially dictates how any of the resultant solar system is going to form, and basically the architecture and what kind of planets there are. We also believe that it played a significant developmental role in Earth and how Earth formed, so it perhaps aided or hindered Earth habitability, depending on who you ask. So basically, Jupiter acts as the sort of like heavy hitter of the galaxy. So whenever there's an asteroid that comes into our system, it reaches Jupiter first because it's so big. And what it does is it slingshots it away most of the time, and then other times it will slingshot it directly towards Earth, which isn't very helpful for us here. So one thing that we do think it potentially did is we think that a lot of Earth's volatiles, so like rich chemicals and stuff like that, which are needed for forming life, were delivered to Earth through an asteroid, so potentially Jupiter helped us do that. And most importantly, these giant planets are very, very rare. They're only found around in, at best, 1 in 5 stars, which is a very tiny amount when you think about how many planets that we have in the NASA archive. There's over 5,000, and only 1 in 5 or 1 in 10 of them have a giant planet. That's pretty interesting. We also know the fact that we are the only, as of now, we are the only habitable planet that we know of. So the potential for sort of creating a system where we can look at giant planets and then see if something habitable forms is a topic that's like pretty up and coming in the field at the moment. So I hope that we've covered enough that I can say that if we want to know about the planet, we need to know the star. And I hope that you've seen from the stellar evolution life cycle stuff that stellar mass has a really profound impact on what's going on. It dictates how big the disk is, it dictates how massive things are. If it's very erratic, if it's very active, it can really prevent or like hinder planet formation. So establishing what's going on in the star is very, very important, and mass has like a big influence on this. And one of the most important things to think about is the evolution of stellar luminosity. So our star is like, our sun is in this very nice and stable phase known as the main sequence, as I mentioned earlier. And that means that luminosity doesn't fluctuate very much. So we have periods of solar flares and stuff like that, but in the grand scheme of things, it's very, very stable. These young stars, it's like the Wild West. They really are very, very active and pretty nasty, spewing out a bunch of stuff as they're getting rid of their disks and things like that. So that can also potentially hinder planet formation. And yeah, and there's also a difference in radiation mechanisms when you look at the different mass of the star. So basically, something like our sun, the main form of it generating energy is through convective methods. And that's basically, if you think about boiling a kettle, all of the hot water rises to the top and bubbles, and all the cool water rises to the bottom. And that's how the plasma releases energy throughout the star. And the other method of this is called radiative, and that's basically when a photon is heated and it takes a random walk. And this isn't a very effective way of putting heat out into the world, because it has to get from the very, very center of the star all the way out, so it takes a very long time. And yeah, it
bounces around a lot, isn't it? Kind of,
it's
sometimes it's going backwards.
Yeah, so it takes a very, very long time to be able to like escape and go out. And this is one of the main differences between a star that is around 1 solar mass versus a star that is twice the size. So at some point this radiation mechanism changes, and we think that has a pretty big impact on how the disk itself is heated and how it moves, which obviously affects planet formation. So I'm only going to show you 2 pretty nasty graphs for tonight, but I will explain it in the best way possible. So here we have planet fraction, which is basically the number of planets that we find, and then here we have metallicity. And in terms of astrophysics, we think of basically anything heavier than like helium as a metal, so take that with a grain of salt if you will. But basically what you can see here, this goes from -1 to 0.5, and there's a very exponential increase, and basically what this means is the more metal rich a star is, the more likely you are to have a giant planet, which makes sense because metals are essentially what we would refer to as dust grains. So if we're thinking of this co-accretion model, the more dust that you have, the quicker that you can build a giant planet, and then at that stage there's probably more gas in the system and it becomes massive much more fast. So that's basically what that means. And then now onto the main talk, which is my promise, the rise and fall of the giant planet occurrence rate. So what you can see here on the x-axis is stellar mass, and on the y-axis is the planet occurrence rate. And you can see that there's a very, very nice function that both rises, peaks, and then falls away. So this peak is somewhere around 1.7 times the mass of the sun. And this is pretty interesting because, as we saw previously on the metallicity slide, the more metal that we see in a disk, we think the more massive the planets are going to form. And that's great, but the most metal-rich stars tend to be more massive because they need to have more mass in the system to first form. But clearly, once you get up to this sort of 2-3 solar masses, they really, really struggle to host a giant planet. And that's pretty interesting because that's very much results that are at odds with each other. So hopefully I'm gonna establish why we think this is the case, why we think there is a rise, a peak, and an increase, because surely we think about, if we're just interested in terms of masses, the more massive the star, the more massive the disk, the more material, the more massive these planets can form. But that's clearly not the case. So hopefully I'll be able to establish why that's the case. So,
well, I'll come back to you just if there are any questions.
Oh, yes. Any questions so far? All good? All right. just shout out, please. Yeah. So now we're on to what I actually do for my PhD. So this is my day job. And I'm a theoretical modeler, so I don't look at observations. I basically take what we know from the observations, feed them into a model, because it's very hard to find these planets, it's very hard to view them, so why not make them on your computer? So my model basically works by, we have something like a disk, like we saw before. We have the star in the middle, we have a disk here, there's accretion onto the central star, there's something called viscous spreading, which is basically how the disk spreads outwards. And basically what I do is I take a protoplanetary core, I place it at a location in the disk at a certain time, at a certain location, and then I say, okay, how big are you going to grow? So I can control a bunch of stuff at the initial outset. So there's a bunch of initial conditions that are really important. So like I said, the birth time of this embryo, the birth location, the initial accretion rate, which is basically how fast this material is flowing onto the star, which is very, very helpful because if you have much more material moving at a faster rate, we think the planets will be able to grow more massive. There's also the initial disk size, so that's disk mass, and then there's metallicity, as I said before, the amount of dust or grains in the system, and stellar mass, how bright the star is, and then the last caveat is that the initial embryo mass is 1% of the mass of the Earth. This is just something that is used in computational models to basically get us started. And then as the disk evolves, we have a photoevaporation mechanism. The one that we use is X-rays, since it's the most well established. So basically, as the disk evolves and the planet grows, it's also losing mass and taking that into account as well as the stuff is getting X-rayed away. So these are a little bit more of what my results look like, okay? So I will do my best to explain. If you have any questions, please feel free to shout out. So on this left-hand side, we have a star around 1.5 solar masses. This one is around 3 solar masses. On the x-axis we have the birth location of the planet, on the y-axis we have the birth time of the planet, and then the colour refers to the planet mass. So what this is basically saying is, if I have a planet that initially forms at 1 million year into the system existing, at 30 AU from the star, then it will grow into be a giant planet of around 1,000 Earth masses. Okay, so we're looking at something about 3 and a bit times the size of Jupiter. So what I would like you guys to take away...
100 times, you said? So
this is times, or...
So the mass was 100 times.
Oh yeah, the planet masses and Earth masses, so it's basically would be up to like 1,000 is this top bar. So it'd be about 3 and a bit times the size of Jupiter, so pretty massive, right? And basically what I would want you guys to take away from this is the fact that this red giant forming region is far more massive and extended around a 1.5 mass star versus around a 3 mass star. Okay, so that basically means that it's much easier to form giant planets when the star is less massive. And this is a good result because it fits in with what we see in the occurrence rate figure that I showed you earlier, but it's also confusing because why is this happening? And the great thing about being a computational modeler is that you can change a bunch of stuff and you can see what affects what. So that's what I've been working on. So I will hopefully help you guys establish why you think this is the case. So if we look at this part of the rise, so we're looking at something that's in between this 1 and 1.7 mass peak. And in this regime, we're still thinking of the more massive the star, the more massive the planet, the more metals there are. And we have the caveat that stars in this regime, they're fully convective. They're still doing this boiling the kettle mechanism of losing heat, which is quite a nice way to retain heat in the system. And the most important part about this is that the disks survive for a very long time. We see stars that have disks that are like 10 million years old, which is a really long time for a disk to survive for. And the longer time that these disks last for, the time scale for giant planet formation is longer because there's more gas in the system, so these planets are able to grow more massive, which is very, very helpful. So if we look at the peak, we want to know why this peak is so special, like what makes it so distinct by itself. So this is another same plot of basically the interested zone that we're looking at is red, and you can see that it's very much large swaths of the graph is red, which means that giant planet formation is very, very good at around the stellar mass. So it's pretty interesting because we think that most giant planets are formed around 1.7. The original paper, I think, said around 2 solar masses, but now it's sort of shifting lower the more observations and stuff we do, which is pretty interesting. And basically, we think it's sort of a balancing act between having a nice high accretion rate that's able to sustain itself for a long time versus having a star that is really, really massive and also has really high accretion rate but exhausts its disk very, very quickly. So there's sort of a balance to be struck between having a long surviving disk, a massive disk, and a high accretion rate to sort of sustain this giant planet growth for as long as we possibly can. So we kick it up a gear again and we go to the fall, which we're looking at the very edge of it, which is around 3 times the mass of the sun, and by 2.5 solar masses, which is about here, essentially this occurrence rate of giant planets is 0, and that's very, very odd. So we want to know why this happens at this distinct stellar mass, and basically we believe it's because stars more massive than 2.5 solar masses, they turn radiative within 2 million years, which means they potentially get rid of their disk incredibly quickly because FUV becomes the dominant mechanism. So because...
Far ultraviolet.
Yeah, far ultraviolet, yeah, becomes this dominant mechanism rather than X-ray, which sort of rules the roost when it's much smaller. And yeah, basically you can see that even with the sort of best case scenario here, which is the sort of conditions that we use, so really, really high disk mass, really high accretion rate, things like that, it's still very, very hard to form giant planets around a star this size. Yeah, so that's basically the conclusion. So we believe the potential origins for the rise and fall comes from this difference in stellar evolutionary tracks. So even something as small as a solar mass, which in terms of we get stars that are 10 times the mass of the sun, but it really, really impacts how these planets are able to form. We also assume that there's a shorter disk lifetime around more massive stars because they're more radiative and they eat away at the disk at a faster rate, so they don't survive for long enough. We also believe there's inefficient planetary migration around more massive stars. And basically that means that around a more massive star, if you have something that forms very, very close into the star, it will vary because the star is more massive, the edge of the disk is extended out and it will reach the edge of that disk and just run out of material. It will never get the chance to be massive. And there's this convective versus radiative timescale, which I discussed, and we do suspect that far ultraviolet or extended ultraviolet photoevaporation could be responsible for the results that we see. And there is also the caveat that we have a binary star problem. So the issue with stars that form in binary are they tend to be more frequent as you increase stellar mass. Stars like to form in groups, but the more massive you are, the more likely they are to form in pairs or triplet systems. And from that, it's very, very hard to form a planet around them. So that's something that needs to be taken into account with these statistics.
So that graph that you showed us earlier with the statistical...
Yeah, the curve.
Is that based on all 5,000 planets?
No, so that one's based off of a smaller sample size that is specifically of giant planets. So I believe it was around 300 stars that they observed in that sample, and it was done at the Lick Observatory, which is in Heidelberg. And basically, they were seeking to find giant planets around giant stars, or in this case, something that's 2 or 3 solar masses. So they did their best
so it's quite a small sample.
Yeah, but even when we look at like the full range of the archive, there's barely any. So originally when we were looking, we found loads of them because they're the easiest ones to find. They're super bright, they're super luminous, but then when we actually delve into doing more observations, we tend to just find rocky planets, which is very, very interesting. So yeah. Another thing is...
So there's a last question about the binary problem.
Mm-hmm.
I mean, do planets form in these binary systems?
So planets do form around binaries. The issue is that when you have a binary system, you would have 2 binary stars, and then you would have either, if they're very, very close together, you potentially have a shared disk around it. So basically the disk is acting like it's one very, very massive star, right? And it'll be like a shared gravity well. Otherwise, they're very, very distant, and they have something called a circumbinary disk, where they have sort of 2 disks that interact, but the sort of gravitational truncation that goes on with them makes it very, very unstable. So it could potentially be a good harbinger for forming giant planets through gravitational instability, because the disks are quite unstable, they're likely to collapse, but otherwise forming them through co-accretion, it becomes very, very challenging, because then you end up with like a 3-body problem and how the planet would be able to orbit or sustain an orbit. And I believe in binaries there's a much higher rate of planets being ejected wholly from the system, because they start to so they're not particularly good environments for fostering any sort of planet formation.
How common are binary systems? Are they the majority, the minority?
I'm not sure if they're majority or minority. I know for a fact that the rate of binaries significantly increases as soon as you increase stellar mass. So because stars like to form in groups and like little stellar nurseries all together, they do kind of become entwined, and then as they become more massive, they can like stick together. There's also quite like a high phenomenon of stars like capturing a binary, so that happens as well if you have like a very massive star in the system and then there's perhaps an evolved star nearby, or like a white dwarf, because it's quite small in comparison, it can get trapped in the orbit. And then very interesting things happen, because as the stars sort of evolve, they like shed material and shed chemistry and stuff like that, so they end up with like sort of another protoplanetary disk or like a planetary nebula surrounding it. So I'm not exactly sure what the exact rates are, but I know for a fact that like they increase exponentially as soon as you increase the mass. They like to form in binaries or in triplet systems together. So yeah. Okay, so one of the advantages of doing a computational model is that you can form these planets as many times as you like, because providing you have the computational power, which is quite helpful. So I do something called Monte Carlo population sampling, and basically all that means is that I take all of my initial conditions that I listed before and I just randomly sample them. I say, okay, these are the expected ranges that we have for these different stellar masses. Go ahead and form your best planet. How many will we form? And basically here we have this is 1,000 simulations for each of these. Around the 1.5 solar mass one, they're are far more giant planets. So basically we have on the x-axis we have the final location that these planets result in, and then on the y-axis we have planet mass. This little green line refers to the point where these planets are considered giant planets. So it's around 90 Earth masses, I believe. Actually, maybe not. I think it's set at like 30 Earth masses, which is the point where it's a giant planet. So anything above it is considered giant. And the colour basically refers to the initial location that these planets are born at. So the blue ones are, I'm sorry, the colour is quite bad here. The blue ones are born beyond 10 AU in the disk. These middle ones are brown and they're born at like moderate locations, so sort of between Earth and Saturn-ish location. And then these orange ones, very, very close in, are born within 1 AU of the disk. And what we can see
inside the Earth's orbit.
Yeah. So basically what we can see is the blue ones become the most massive. And that's basically because they have the longest way and the longest time to migrate in the disk. So they're going to acquire the most mass. Versus the ones that are sort of these orangey ones, which form very, very close in. So they probably have to form very, very quickly to escape this photoevaporation, losing mass and stuff like that. And they're not able to migrate very much. So they probably just become giant planets and no more, basically, by definition. So yeah, and from this we can see that there's still way more giant planets forming around 1.5 solar masses, much harder to do around 3 solar masses. And yeah, so that's another thing that we were interested in, because these far distance ones, because they take so long to form and they're so massive, it usually happens in quite a metal-rich disk, so that they have time to be able to grow and migrate and things like that. So yeah.
Am I misreading that graph? It just seems there's still quite a large number of giant planets at 3
Yes.
solar masses.
Yeah, there is quite a lot. So this is the isolation mass. So it's 30, like I said, like 30 Earth masses, and there's probably slightly more in the 1.5. But if you want to think about the true giant planet population, which is probably anything above 100, there's a much higher concentration around the 1.5 solar masses. I probably should have adjusted that line. I'm sorry. Yeah. And yeah, some of the future work that I'm hoping to explore is basically looking at different chemicals in the disk, because a lot of the research at the University of Leeds is focused on disk chemistry, which is very cool. And basically we have it set up at the moment so we can track the amount of water that would form in a planet core. So this is again birth location, birth time, and then the colour refers to the amount of water that you might find in a planetary core. So if something forms very far out, you get a very water-rich core, and then something closer in, because it's heated by the star, it's evaporated away. So you get a very dry planetary core to form things. And basically you can do this with a bunch of other chemistry, and this helps you track how planets form in disks, which is basically one of the good precursors to JWST and also to the aerial launch, which is coming up in a few years' time. So yeah, I hope that I've managed to cover everything. So the main findings that I hope you guys are able to take away from this is that giant planets are less likely to form around more massive stars. Planet migration around more massive stars is less efficient, and this makes growth difficult, and especially at large orbital distances. Planets that are born far away from their host stars are able to grow the most massive, and metallicity is a very important factor in deciding how massive a planet can grow. So, thank you.
Thank you very much.